for the differentiability at the origin. The differentiability at the origin doesn't exist. You already know. You already stated this previously. So the domain for the continuity and differentiability for this function is going to be R2 except 0. And except 0 is coming from the first component, which is the root of x squared plus y squared. Once more, continuity and differentiability domain of G, as I told you. Continuity of G of F, which is root of x squared, it's continuous in R2. Remember, but it's not differentiable at the origin. So the continuity and differentiability domain will be R2 except at 0. Okay? For the vector valued function, in order to be able to work with the first component and the second component. Any questions? Now, operation involving differentiable functions. In operations involving, in general, what are the operations, Hamza? Hazan, I'm sorry. Addition and subtraction, am I right? Or, as you will say, the product or the composition. Remarking, in the addition or subtraction, if you have two functions which are differentiable, then their addition will be differentiable. If you have a product, f and g are differentiable at A, then f dot g is also differentiable at this point. Also the composition, if f is differentiable at A and h is differentiable at f of A, then the composite function, h composite f, is differentiable at A. Of course, Mr. Saif, he had to state that f is differentiable at f of A because you are studying the case of h of f at A. So first of all, f is going to be differentiable at A and the h should be differentiable at the whole value of f of A. You understand what I'm saying? بجد واضحة؟
Yes.
Okay, once more. Then you have a composite function which is f of the function of A. So A actually enters f, that's the condition for f to work, and the f of A, which is the value of the function at A, is the condition as an input for the outer function, which is h. Okay? So these mainly are the operations involving the differentiable functions, as you can see. Okay. Domain of differentiability for polynomials, exponentials, logarithmic, trigonometric functions, it will be the main domain. There is no problem in all of this. I mean about the general functions as you saw. Do you remember the previous problem? We have x plus y, which is a polynomial, so we didn't face any problem with it. And we had just only to look to the radical, which is the root of x squared plus y squared. If it was the root of x plus y, it will be continuous within and differentiable within insular. Okay? So mainly any function f given explicitly by an expression built out of polynomial, exponential, logarithmic, trigonometric functions by the usual operations, addition, subtraction, multiplication, division, composition, is differentiable in its entire domain. There is no problem with it. Okay, once more, if the expression also contains nth root, زي اللي احنا شفتها, root of x squared plus y squared, I have to stop and look carefully at the differentiability at the origin. Okay? And then once you are trying to identify the domain, we excluded the part where the function has problems of differentiability at the origin. Okay? This is why the previous problem it was R2 except 0 and 0. Okay, the absolute value, or more generally, the norm of a vector, I will have to study it using the definition and step by step. Okay? So once more, all points where the argument of any root absolute value or norm is equal to 0 are not always part of the domain of differentiability, and they need to be investigated separately, as I told you. I need to focus with them and study them. Results involving differentiable functions, f, a vector valued function from Rn into Rm, and the A belongs to the interior of your domain, which means a point in your domain. Then f is differentiable at A, then f is continuous at A. So the condition for the differentiability at A is the existence of continuity. If we are running from Rn into R, which is functions in several variables, If f is differentiable, then any partial derivatives of f exist. If you remark Hazel, this is what I depend on in answering the second part in the previous problem. When the partial derivatives doesn't exist, then the function is not a differentiable, okay? And the third part, if f has n, the n first order partial derivative of f is differentiable at all points at which at least n minus 1 of these partial derivatives are continuous. So this is mainly the main theories that we rely on in generalizing the results or dealing with the functions either in several variables or the vector variant functions. Okay, this problem also is really very nice. I want you, and also we already did it, not in the previous lecture, but I believe in the lecture after, before it, okay? So he wants you to consider f from R2 into R. And this is also an example who came previously in other exams, and you should choose the correct answer, but the steps is really very simple. He gives you, remember, he gives you the value of the function at the origin. And it is equal to the first partial derivative at the origin. Both of them is equal to 0. So the definition of the function and the partial derivative is equal to 0. And the partial derivative of f with respect to y is 2x times y squared. Remember or remark that he didn't give you f of x and y. He didn't give you the function. But he gave you the values of the function at the origin and the partial derivative formula. But the main function is not given, okay? Continue. He wants you to justify that f is differentiable function at the origin. How to justify this? If you remember, I have to get r of x and y, the limit of r x and y with the norm, and is equal to 0. So all I have to do is to use this relation. If you don't remember, this is the relation that I'm using. F of xy equal the value of the function at the origin, and all of this is what I told you about. It is the gradient vector of f at the origin dot x minus a, y minus b, plus a remainder term of x and y. So this is mainly your function plus f at a and b, and this is f of x and y, the condition for differentiability. The general one. So all I have to do is to find the value of r. From here, Mr. Muhammad, it's directly and given that the function at the origin is equal to 0. So this part is equal to 0. Partial f partial x at the origin is equal to 0. So all of this part cancelled. And also, partial f partial y, it is 2xy squared. If you make a substitution by the origin, you will have 0. So all this part also tends to 0. Now I have r of x and y equal to the value of the function, which is f of x and y. So all I have to do at the time being, and this is the result, let's give it. All I have to do is to find the differentiability, but stay by stating this term. R of x and y divided by the norm of x and y. Remark, Muhammad, I don't have to exert a lot of effort because you already know that the value of the function at the origin is equal to 0. So the limit, this limit of x and y tends to the origin. It will be 0 over the norm of x and y, which means 0. The limit is equal to 0, which means the function is differentiable. That's the theory that we are working on. You have to review these parts, and as I told you, you will feel it is direct. There is no problem with it whatsoever. But you will have to review. This is very, very important. You will have to go through the lectures, lecture by lecture. All of them, you will find them making a very good sense. Okay? So once more, as I told you, just making the substitution will let that r of xy is equal to the value of the function. Once, Muhammad, you use this relation, it's going to be 0. Over anything, it's equal to 0. So the limit will really exist. That's exactly the what's the theory tells us? If the limit of r of x divided by the norm is equal to 0, then the function is differentiable. Okay. What's a C-class function? A C-class function means a function is differentiable up to k times. So, Mr. Saif, if I told you this function is a C1 function, what do you understand? The first derivative, it is differentiable one time. Okay? But if I told you it's a C2 function, which means you can differentiate it how many times? It's 2 differentiable up to 2 times. So a generalization for this idea, k times, it means your function is differentiable 2k times. So once more, if f is a ck function at a, if all its partial derivatives up to the k are continuous at a, if f is ck, it also is ck minus 1, ck minus 2, and so on. Which means, if I told you the function is c2, it means it's a c1. If the function is c3, it means it's a c2 and c1. And it makes sense, because c3, it means it's differentiable up to the third derivative. You understand what I'm saying? So you already did the second and the first one, okay? So it's really a very direct theory. Also, a generalization for this guy, if you have Rn into R and the A belongs to the interior, if f is C1 at A, then f is differentiable at point A. This is the relation of the directed directional derivative. We talked about the directional derivative previously, and how to get a directional derivative by the 3 main steps. Get the gradient vector, okay? Get the vector of the function, multiply them dot product, you will get the directional derivative of your function. I'm talking at the time being, at the directional derivative, but in the case of Rm. So instead, I will have the gradient vector, not in 2 dimension, up to n dimension. And in this case, I will multiply it by the unit vector, which is gonna also contains in the components. And that's the direct formula for evaluating the gradient vector or the directional derivative as a generalized form. بص على the problem D, which is really a very good problem. He is giving you, consider the function f, which is running from R2 into R. Of course, it's a piecewise function. It's a piecewise function. Okay? It has 2 branches. The first branch, Mr. Muhammad, is x squared over y. X squared times y divided by x squared plus y squared, which is a rational function. Mr. Hazan, please turn off the air conditioning, please. So the first one, it's as you can see, it's a rational function in 2 dimensions. But if you remark, it is valid and applicable where this one, when x times y is greater than 0. When x times y equals less than 0, when is going to happen? It is in the second, yes, you are right, it is in the second and the 4th quarter. Because if you remember, we have 4 quarters. This is Q1, that's Q2, and Q3, and Q4. In Q2 and Q4, x times y is greater than 0. X and y times y is greater than 0. But in the first and the third, you will have x, y greater than 0. Most of them are positive, the values of x and y. And for the elements in the third quarter, all the values will have negative values or negative components for x and y. Once you multiply them together, the result will be positive. So if I'm telling you that x and y is greater than 0, I'm talking about the first and the third quarter. X, y greater than 0, I'm talking about the second and the 4th quarters. Okay? Okay, I want you to define the continuity domain of f. I want you to define the continuity domain. Okay, state and justify whether f is differentiable in R and 0 up to the second derivative or not. Is it differentiable or not? Okay? And not just only this, he wants you to evaluate the gradient vector of f at the origin and to find f dash at 1 and negative 1, which means the directed derivative of f in the vector direction 1 and negative 1. Are you with me, Mr. Muhammad? Okay. Using the results of C, Mr. C, show that f is not differentiable at the origin. It's, as I told you, it's a very good question, covering a lot of points altogether. So let's start with the first part. I need to discuss the continuity. So now I'm going to focus with the second and the fourth, quartils, the first branch. Then I will focus with the case of the first and the third quartils. So if I'm talking about the second and the fourth quartils, it means I'm working with x squared y divided by x squared plus y squared. And this function in this region is defined, okay? And the limits exist, which means it's continuous at all the points. The only point that may cause problems is the origin, because there is no division on the origin, am I right? On 0 and 0. But if you remark, it is excluded from this domain, because this domain deals with the value of x and y, but less than 0. So you can't use 0 over here, so you are in a very good shape. So this function is continuous, as I told you, continuous everywhere in the second and the fourth, quarters. There is no problem whatsoever. If I'm working with the first and third quarters, I will have to deal with this guy. Also, it will have no problems since x times y is positive, because the argument of the logarithmic function should be greater than 0. So I'm giving you x and y plus 1, which means you will never hit 0. Am I right? This is why, yes, you will never hit 0 for the argument, because at the border, which is xy equal to 0, you still have 0 plus 1, which is 1, and 1 is equal to 0, which is a defined quantity, which means you don't have problems elsewhere in this case. Even on the boundaries, okay, you don't have a problem. Even at the origin, you don't have a problem. So, bottom line, the function is continuous on all of R2. The second and the fourth, they are very good with the rational function that you are using. And the second and fourth. The first quartile and the third quartile, they are okay with the existence of ln xy plus 1. The existence of this positive one forbidden the problems or eliminated the problems that will be generated once you deal with the origin. Okay? So it's very simple. Okay. The set of R0 up to 2 means x doesn't equal to 0 and y doesn't equal to 0. So we are away from the axes anyway in xy. This is why if xy less than 0, rational function, smooth, infinitely differentiable. If you have a rational function like 1 over x, and you are away from the origin, it will be differentiated up to infinity. It's going to be x to the power of negative 1. Differentiate negative x to the power of negative 2. Differentiate more. It's going to be 2x to the power of negative 3, and so on. So it's differentiable at infinity. Same like limits y plus 1 as long as you are away from the origin. So for the function that's this piecewise function, it's a C2 function with no problem. The only problem that will may happen at the origin. So the differentiability domain is R except the origin for the second derivative, and they can go for more than that. Okay? This is the main issue. So the boundary issue, the only potential problem is that xy equal to 0, but this is excluded from the beginning. The function is differentiable everywhere, so we don't have any problems with this. Okay, I need to get the gradient vector at the origin. Muhammad, do you remember the function? Look to the function. Your function is x squared plus y squared, y and xy less than 0. But if x and y is greater or equal to 0, this is going to be the function, which means safe. If I want to get the gradient vector at the origin, I will use the arm of the function, which contains ln of xy plus 1, as I told you. This is the only one that I'm going to use. زي ما شايف الموضوع صعب. لا بس انا So So once more, as I told you, this is the first part. Let's deal first with this one, for this part of this problem, and then I will go to the second one. Okay, for this part, as I told you, I will deal with the logarithmic function, which was len, am I right? Len of xy plus 1. Okay, so I will try to get the gradient vector, but unfortunately, of course, the gradient vector, as you know, it is partial f, partial x, partial f, partial y. I can't get the partial derivatives directly because I have a piecewise function. So I will use the definition. This is the definition of the derivative in the direction of x. Can you see? I'm dealing with the definition with x, so I'm using the x value. I'm dealing y. When you are dealing with y, you are changing the k value. If you do this and you make the substitution in len xy plus 1, you will find that the limits already exist. It's going to be len 0 plus 1, which is len 1, okay, minus 0 over h, which means you will have 0 over h, which is 0. That's before you, the direct result from this guy, before even applying the limit. It's going to be len 1 minus 0, which is 0, divided by h, which is going to be equal to 0 without even approaching the limit. You understand what I'm saying? And the same result will happen in the k direction. It's going to be exactly the same. So this is the k direction. You will have limit len 0 plus 1 minus 1 over k. Why safe? Because the function is still xy. So if you use h0, it's going to be h times 0. And if you use 0k, it's going to be 0 times k, which is in both cases equal to 0. 0 plus 1, which means len 1 is equal to 0, as I told you. So the partial derivatives already exist, and the both of them equal to the origin, or I'm sorry, to 0. So that's for the first, the gradient vector. I have the gradient vector. Now I have it. The second part of our question, he wants you to get the directed derivative in the direction of the origin. And also, there is a trick in this part. He wants you to get the directed derivative in the direction of the vector 1 and negative 1. In order to get the directional derivative, you found previously, I'm using the direct relation. The direct relation of having f of u at certain point is equal to the gradient vector, which is at 0 and 0, times the u as a unit vector, as this guy. I'm using this relation. This is applicable once your function is differentiable. Once this function is differentiable. Okay, you understand what I'm saying? But at this point, but if the function is not even differentiable at certain point, I can't use this relation. So I will use the general relation. First of all, I will get the unit vector of this guy. In order to get the unit vector of the vector 1 and the negative 1, all I have to do, as you know, in order to get u divided by the norm of u, is to divide 1 and the negative 1 by the magnitude of this vector, which is the first component to the power of 2, plus the second component to the power of 2, which means it's going to be 1 over root 2 and the negative 1 over root 2. All of this, we already did it previously. So once more, this is the normalized form, 1 over root 2, negative 1 over root 2. Then I will use the definition, which is limit t equal to 0, f of t by u, minus f dot 0 over t, which is going to result to, once you substitute by tu, which is t over root 2, minus t over root 2, I will use, in this case, using those guys, I will use the branch which contains 2xy divided by x squared, y squared. So, in this case, x times y is less than 0. This is why I will use the value of the function x squared y divided by x squared plus y squared. Muhammad, make a substitution. And instead of every x, I will use t and root over root 2. And then instead of y, I will use negative 2 over root 2 in negative t over root 2 in all the kernel and simplified. Once we do this, then the function, as you can see, that's the denominator, which is x squared times y. That's the denominator, which is x squared plus y squared, which is relative to t squared. F, it is the division of the numerator and denominator, which is negative t over 2 root t. Now I have the limit. Okay, so once more, the directed derivative of negative 1 and 1 at the origin will lead to the value of negative 1 over 2 root 2. I had to add this, our problem is already ended at this point, but I had to stress on this in this result. Why we can't use this formula, this is what I told you about. Why not to use this guy? It's much simpler. But if you use this guy, the result of your vector, or your the directional derivative is going to equal to 0. If I use this relation. So why the contradiction? Because f is not differentiable. Okay, so once more, as I told you, if I try to solve the problem using this relation, this formula is valid only when it is differentiable. So f of xy, so if it is differentiable, I can use this approximation. This is why this relation is successful once f is differentiable. So this function satisfies partial derivatives. Directional derivative exists in that direction, but not differentiable at the origin for this function. Since it's not differentiable at the origin, then I can't apply the direct formula in order to get the directional derivative. I would have to go through this node, to go through this guy. I have to use this guy in order to get the directional derivative of our function. Remark, the gradient exists, but doesn't control directional derivative, and that's a very, very nice one. Schwarz-Young theorem, we already know it previously. If your function contains partial derivatives, is differentiable or continuous, the mixed derivatives will equal to each other. So getting partial 2f partial x partial y, it will equal to getting partial 2f partial y partial x. That's about the mixed derivative. So once more, if f is such that running the domain of f, it's completely contained from Rn into R. The partial derivatives f double xi xj and f xj xi are the same at all points at which f dash xi and the f dash are differentiable. So nothing more. The last thing in the differentiability part, it is the direction of the maximum growth. The direction of the maximum growth. It is exactly like the relations that we saw previously, but with just only one twist. The direction of the maximum growth will happen when you use the vector of the gradient vector. When you consider finding the directed derivative at the gradient vector. Thus, the maximum will happen when f dash, okay, which means your function or the directed derivative of u at a, u is the gradient vector by itself. In order to make this problem very obvious for you, let's solve this problem. You have a function in xy, which is 3e to the power of xy minus 1 plus x ln 1. He wants you to show that 1, 1 belongs to the interior domain. As you can see, this function is defined for the first part where x times y, where y is positive. This function is defined while y is positive. So it is defined for the upper domain, all the values of the upper domain. 1 and 1 already belongs to the upper domain, so it belongs to the interior of your domain. There is no problem with that. He wants you to define the differentiability domain of f. So the first step, show that 1, 1 belongs to the domain. Our function consists of two parts. The first part is exponential, there is no problem with it. The just only limitation exists in lim y, and y will be okay if I'm sorry, the arithmetic function will be okay while y is greater than 0. So you're really very good. It belongs to the interior of your domain. There is no problem with that. The differentiability domain for the first part, it is smooth everywhere because it's an exponential function. The other function, which is x and y, also a smooth function since you are away or you are satisfying that y is greater than 0. So also it is differentiable with y is greater than 0. So now for a and b, it's okay. You want you to state and justify which are the vectors u and v and r2 with norm 1 and such that f dash u and v 1 and 1 is maximum. In order to get this, I will have to find the gradient vector. In order to find the gradient vector, I will need to get partial f, partial x, partial f, partial y at 1 and 1 for each one of them. So let's start by getting partial f, partial x. How to differentiate? Differentiate with mean term. It's gonna be 3 times e to the power of xy minus 1, but don't forget times 1. I've differentiated the first part of this problem with respect to x. Then I will continue differentiating the second part, which is going to be plus. Differentiating with respect to x will lead to ln 1. I will do exactly the same hassle, but with respect to y. So let's do it together. The first part will be 3. The exponential part will be e to the power of xy minus 1, but I'm differentiating with respect to y. So it will add x, okay? Then plus, I have x times then y. I'm differentiating with respect to y. So it's gonna be x over y. These are the two guys, okay? Now, safe, start substituting by 1 and 1. Replace x and y by 1 and 1. So once more, you will have 3e, I think. This is x and, this is gonna be 1 minus 1 equal to 0. So it's gonna be 3. Then 1 is equal to 0, so it's gonna be just only 3. For the second one, it's gonna be 3 also. And the x over y is gonna be 1, so it's gonna be 3. So it's gonna come up to 4. So your gradient vector at 1 and 1 for f, your gradient vector at 1 and 1, it's gonna be 3 and 4. Can you put it on a normal form or can you normalize it? Yes. How to normalize it? I will divide the components on the square root of the square of the first component plus the square of the second component, which means the unit vector that I'm dealing with is 3 over 5 and 4 over 5, because this guy is equal to 4. That's the vector. Do you need the directional derivative in the direction of the maximum? Okay. Then f at 3 over 5 and the 4 over 5 time of the function at 1 and 1. This is going to be your value, as you will see. So all I had to do is to do these steps and I will be able to get the value of the maximum gradient vector, as you will see in the coming slide. Once more, let's do all of these relations. So as I told you, that's the gradient vector. These are the two components. Substitute by 1 and 1, you will have 3 and 4, exactly as we did. So the second step is to get your vector, which is related by, divided by the magnitude, which is 5. So the maximum direction is 3 over 5 and 4 over 5. If you want to find the value, just multiply the gradient f at times u, which means 3 over 5 and 4 over 5 times 3 and 4, and the result will be 5. Thank you very much for listening to this part, and we now finish the first of our lectures today. Please, I want you Please, this is really very important. At the time being, in order to review this part, especially, I know you were really very busy in the previous period. We had Ramadan, we had the Eid, the Jam Nasim. I believe you had everything. From Kahk, from Ringa, from Sir, from whatever. Okay? Now I need you to focus. You will have to review the last parts. we are talking about differentiability. So mainly we are talking about derivative. We already started by the limits. After limits, either the limits in one dimension or the limits in n dimension. The limits in n dimension, I had the directed method, I had the iterated method. Then we have Cauchy method, which is the epsilon and the theta and the delta definition. After finishing this part, we went through the continuity, either in R or in Rn. Then after both of them, we started working with derivatives, understanding the existence of partial derivatives in nth dimension. After making this part, or doing this part, which is not difficult, we went through the definition of the Jacobian and the gradient vector, because we will need them in functions in several variables, as you saw, or in vector valued function. After all of this, we went through the discussion of differentiability. And this discussion was in the previous lecture. After this, we went through properties of differentiable function, where we covered the limits today, how to use Cauchy's limit, the differentiability in Rm, and as you can see, it's a connected part hazard. So you will have to study it from the beginning. Our second lecture, I will leave you for 10 to 15 minutes, just to move around. Then come back to me. I will start today the antiderivative or the integration. It's very, very simple, not even comparable to all of this, but you have to understand it from the beginning. So please, just take the 10-15 minutes if you want to pray, if you want to grab something or get a coffee or something, and then we will get back. Thank you very much for attending, and we will. Okay? Thank you.